Yeah.
Did you miss me?
Of course.
That's the right answer. Yeah. Yeah. So how's vector starting out?
It's not too bad. No.
Yeah. Okay. Any questions?
Not as of yet.
Yeah. So if you've done, yeah, if you've done
Okay.
physics, like you've done force as a vector.
Yeah.
Yeah, a little bit of trickiness with the inclined plane. The force times sine of theta is parallel to the ramp and all that stuff. But generally speaking, the problems fall into a couple categories, so they're not too bad.
Okay.
And we were going to do velocity today.
Alrighty.
All right. Lindsay's almost ready. So Lindsay's just done the kayaker across the river, and kayaker's going 4 kilometers. Kilometers an hour or meters a second? Meters a second. I don't know if that's realistic or not. And the river's going 3 meters a second. So this is north, and this is west. Yep, there we go. And it's just asking you for the bearing in this case. And in this case, it's a right-angled triangle. So it's just arctan 3/4. It's going to give you exactly what the bearing is. And I really just have one sort of sample problem to go over. And it's very, very similar. Really, in practical terms, the only difference between the airplane problem and the boat crossing the river problem is that the airplane problem is not a 90-degree triangle.
Mm-hmm.
So here we go. You've got an airplane. It's got an airspeed of 200 kilometers an hour. I think that's realistic. Wind is blowing 50 kilometers an hour, south 45 degrees west. And so these are always a little bit awkward, but it means you start from the south and you go 45 degrees in the direction of west. And the big question is, what bearing should you take if you want to go directly north? Okay. So some of them are, some of the questions often say, it gets blown off course. What's the result? But if you're a pilot, really, you're not interested in getting blown off course and then trying to figure out where you are.
Mm-hmm.
You're really a lot more interested in knowing exactly what you have to do to go where you want. And so in this case, the resultant vector needs to be the one that goes to the north. So I've kind of drawn the triangle. What should go on this side? Anybody? Anybody? Oh, Lindsay just waved me off. Any guess? Jeff, what should go on this side?
On the...
So yeah, this one right here.
That's the... my brain's not working right now.
Oh, okay.
I need a minute.
That's okay. Plus, you're kind of... This is going to be the wind. And so the wind is blowing south 45 degrees to the west.
Oh, okay. Okay, there we go.
Yep, so that's the vector, that's the wind vector, okay? Really interestingly enough, we'd call that a northeast wind, but it's blowing towards the south 45 degrees. Yeah, I know. It actually plays with my brain quite a bit. Yeah, and so this is the, I'll just fill this one in. This is the 200 kilometer an hour. So this is the airplane flying 200 kilometers an hour. The air itself is actually blowing the airplane off course. And so the airplane wants to have this resultant north vector right here, okay? And so this wind is going to slow it down, and it's going to blow it towards the west a little bit, and we have to figure out what's going on in order to get the exact north vector as a result. So this one's actually not too bad, at least to start with. Care to guess what? Uh-oh. Maybe it's harder than I thought. Okay, so this is 45 in here. This is 135 degrees right here. Okay, I know that for sure. Does that make sense?
Yep.
Okay. And really what I want to know is this angle down here, this theta. It's not a right angle triangle, so we aren't using SOHCAHTOA. We're down to cosine law or sine law. And I really prefer sine law over cosine law. That's a personal preference of mine.
Yeah, me too.
Which one does it look like? We know this angle across from 200. We know this angle across from 50. Yeah, that's right. So 200 over sine 135 is equal to 50 over the sine of theta. Okay. I don't think we're going to run into that ambiguous triangle issue that you sometimes get into because we aren't actually calculating an angle. If we were calculating an angle, we'd have to worry about the ambiguous triangle problem, the pariah of all times. So 50 times sine 135 divided by 200 is equal to 0.1767. So we just use arcsine to figure out what that angle is. And it's 10 degrees. Okay, so that little bitty angle in there is 10 degrees, which really amounts to quite a bit if you think about it over a fairly short distance. So the second part of the question is really just asking us, what will your actual, oh, sorry, shouldn't say airspeed at all. What will your ground speed be? In other words, how fast are you actually going relative to the ground? Which is going to be, yes, our resultant vector right there. And if this is 10 degrees, and that's 135 degrees, that one is going to be 35 degrees. And at this point, when I go to solve the triangle, I know I can't use SOHCAHTOA. I don't want to use cosine law because I always get it wrong when I enter it into my calculator. I think we can go with sine law for this one. Everybody agree? Sine law, thumbs up? Thumbs up.
Yep. Oh, yeah, it should be good.
A lot of these wind up being cosine law. A lot of the vector problems are cosine law, but we can deal with that. So 50, let's go, yeah, okay. 50 over the sine of 10 degrees is equal to x over the sine of 35 degrees. So x is going to be sine 35 times 50 divided by the sine of 10. Sine 35 times 50 divided by sine 10. And so as it turns out, stupid wind, we're actually only going 165 kilometers an hour, which if you ride your bike, you really learn how to either love or hate the wind. Hate the headwind anyways. Wind is much more significant than you ever give it credit for. It's not so bad if you're driving a car or a tractor or something like that, but when you're on your bike, flying in an airplane,
Yep.
makes a big difference. That's, let's see. Oh, I think that's roughly all I wanted to talk about. A lot of these triangle problems are, you just set them up and solve for the sides. The CEMC exercises also tend to switch back and forth between the velocity triangle and the displacement triangle, okay? And so the velocity triangle and the displacement triangle, they are similar triangles. They're just sort of the displacement triangle is the velocity triangle multiplied by a factor of t. Okay, so sometimes they're switching back and forth. So, if this airplane was traveling for 2 hours, for example, this would be a 400-kilometer side. This would be a 50-kilometer side. Sorry, this would be a 100-kilometer side, and this would be a 330-kilometer side.
Okay, I gotcha.
Yes, so sometimes...
Because it's just kilometers per hour, so you'd multiply it by the hours and the units would cancel.
That's right. And sometimes some of the problems actually involve t. Now, just so you know, when we do our test, I'm probably just going to leave it as velocity triangles. I probably won't turn them into displacement triangles partway through.
Okay.
Yeah. So that'll be that.
Alrighty.
I'm just really quickly going to introduce what they call the algebraic, or sometimes what are known as Cartesian vectors. Just really quickly, because I'm going to be away for the next couple days.
Yeah, no, for sure.
And the Cartesian vectors, I don't know, they're really easy. I think they're actually so easy people don't believe they're doing them.
It's good to hear.
Yes, it is. It's a nice little break. Okay. Unfortunately, I do not have a grid, but I'm going to draw this Cartesian vector or algebraic vector. Oops. Okay. So there it is. It's called 2, 1. You'll never guess what the 2, 1 represents.
Coordinates?
Yeah, they're just coordinates. Yeah. So if this was at 0 and 0, the tip would end up at 2 and 1.
Okay.
Okay. So far, so good, right?
Yep.
Okay. I'm going to, yeah, close enough. Good. Take a guess at what this vector would be. Just, I roughly drew it, but it has integer values, this algebraic vector.
Is it like relative to the other one?
Yes, I've tried to draw them roughly proportional.
Okay, so wait, is it on the same grid?
Yes, pretend it's on the same grid.
Okay, gotcha.
Yeah. And it doesn't actually matter. Keep in mind, it doesn't matter where the position is. It's just sort of.
Well, the y, maybe the y will be 1-ish.
It's 1-ish, yes.
Yeah, it looks like it's, and then the x would be just.
Yeah, so it's actually 1 and -1. Okay, there we go. So if I called that one u and that one v, this is 2, 1. This is 1, -1, sitting out on the grid. Okay.
Okay, I see what you mean.
Yep. Get ready. U plus v. So this is vector addition.
We go. You just add the points, or?
Yeah, you just add.
Pretty much, I guess.
3 and 0.
All right.
2 plus 1 is 3. 1 minus 1 is 0. So that's vector addition. Vector subtraction is also equally easy.
Yeah.
So what about this? I'm going to multiply u by the scalar 3. And it's not going to be 2, 1. Guess what it's going to be?
It's going to be 6, 3.
6, 3. And so that's scalar multiplication of algebraic vectors.
Okay.
And that's actually it.
Alrighty.
Yeah.
Yeah.
They do put them on the grid, and you know, you start at A and you end at B, and what's the algebraic vector? But really pretty easy stuff.
Alrighty.
And yeah, so that's the next 2 days. We don't have a test for like until way on and next week.
Sounds good. I'll just keep doing the questions when I guess get comfortable with this.
Yeah. Yeah. Perfect. All right.
Alrighty.
Well, wish us luck. Spencer the Butcher Bennett's just sitting right back there now.
Nice. All right. Well, good luck to you guys.
Okay. Good. We'll talk to you later.
Yep. Have a good one.
Bye, Jeff.
See ya.